Hello everyone. So in this lecture, we are going to discuss about branch and bound. So first of all, I would like to tell you the difference between the backtracking approach and the branch and bound approach. So as you can see that we have a state space search tree, right? You know that in backtracking, we form a state space search tree. Similarly, in branch and bound also, we are going to form a straight space search tree. But the approach of finding, or I can say the approach of traversing this state space search tree is different in both the approaches. Okay. So first of all, I would like to introduce with the basics of backtracking. So in backtracking, the motive is to find the feasible solution. So what we're going to do, we are going to just travel in a depth first search manner from top to down, and then we will see that whatever choices we have made, whether it is going towards a feasible solution or not. If it is not going towards feasible solution, then what we will do, we will undo our step, or we will move back and we will move to another path. So in backtracking, we are generally pointing to the problems which is concentrated towards finding the feasibility solutions, right? However, in branch and bound, we are more concentrated towards the optimization problems, okay, like minimization, maximization. And then again, in branch and bound, we are going to solve the minimization problem. And if we encounter a maximization problem, like in 01 knapsack, we have to maximize the profit. But in branch and bound, we are going to this optimization problem by modifying its definition so that it is converted into a minimization problem. So taking the profit rather than in positive numbers, we will take it in negative numbers. Now, automatically, as we convert the profit from positive to negative, the problem of maximizing the profit will be converted to minimizing that profit, because it is being converted to negative numbers. And then when we solve the problem, we find a solution, we can turn the sign back and we can make this negative number again to the positive. So inherently we get the maximized output. Next, in branch and bound, we travel in breadth first search and depth first search manner both. Look, what's the basic approach? We'll go level by level, but within a level, we'll choose a node which is going to give us the optimal solution. We'll explore that node first, and then we are going to explore. Say in this, we have 1. Okay, 1 is the root node. We are going to start with 1 as the root node. Now, we will explore 2, 3, 4, all the children of 1. Okay, now using some cost function, we are going to identify the cost of these nodes, or cost of including these particular path in my overall solution. Say if the cost here was 10, here was 8, and here was 12. So obviously 8 is my minimum number. So the node which I will explore further will be 8. Now I'm not going to explore 5, 6, 7, 8, 9, 0 all together. Rather, I'm just going to explore 7 and 8. That is the child nodes of the 3. Then I will explore them. I'll calculate the cost function related to it. Say it was 18 and it was 20. Now again I'll repeat the procedure. I'm not going to explore the child nodes of 8. I'll explore the child nodes of 7. So this is the approach I'm going to follow in branch and bound. Now, the very first example we're going to consider in this branch and bound is traveling salesman problem. Say we have 4 nodes, or we can say these are 4 cities. A, B, C, D are my 4 cities. Okay, and a person has to travel from one city to another, then from that city to another city. Likewise, he has to travel all the city such that the cost of traveling is minimum, and it then return back to its source position. Now, how the weight or how the cost is considered in this? So we just assume that we have a graph and these cities are the nodes of graph. So A, B, C, D are the nodes of a graph. Now, traveling cost from A to C is represented through an edge that is from A to C and whose cost is 12. So I'm labeling this particular edge as 12. Now, traveling cost from C back to A is 11. Now, I can draw all other edges. So, assume that this is my complete graph. And my salesman has to start from A and travel to B, C, D, whichsoever path gives the minimum cost and come back to A. So the problem states that a salesman has to visit every city exactly once. No, he's not going to visit any of the city twice. So this is the first constraint. Then he has to come back to the original source city. So if I'm starting from A, then I have to come back to A. If I'm starting from B, I have to come back to B. Then I have to explore the shortest path, the shortest route among the every possible route here. So we will now see how I'm going to solve this problem. So first of all, we are going to present the graph in form of a agency matrix. So to construct a agency matrix, what we have 4 by 4. As we have 4 nodes here, if we had 5 nodes, we would have constructed a 5 square matrix now. So we have created a matrix having columns A, B, C, D and rows A, B, C, D. Now, every entry in this matrix will define the path from one node to another node. So the path from the node lying in the row to the path lying the column. Fine. So if I'm talking about this entry will give me the path from A to A. This entry will give me path from A to B. Likewise, all the entries will give me the path. Now, one thing more. If I am at A, there is no cost associated if I'm going to travel to A only, right? If I am at a particular place, there is no cost associated with traveling to that particular state only. So here is the matrix. So we have just defined infinity for A to A, infinity for B to B, infinity for C to C, and infinity for D to D. Every other entity is defined as per denoted in the graph. So as you can see, for traveling from A to B, I have 4 costs, right? So this edge is represented here. From traveling A to C, I have a cost of 12. So this is the edge over here. So this is how my agency matrix is going to be represented. Now how I'm going to solve this traveling salesman problem. To solve this traveling salesman problem, I have to reduce my agency matrix. So first of all, what is this reduction and what is the purpose of this reduction? So first of all, I'm just going to explain you what is this reduction or how I'm going to perform this reduction. So to reduce a matrix, say this matrix or this particular agency matrix, I have to reduce it row wise as well as column wise. So in both way, I have to reduce it. By reduction, I mean that there should be at least one entry that is 0. So in each row, there should be 1 0 and each column, there should be 1 0 entry. Now, how I'm going to do this? Let's see. So now to reduce this matrix, we will first reduce the rows. To reduce the rows, we have to make one entry 0 in each row. So we'll identify the minimum number in each row and then we will subtract that particular number from each entry of that row. So in first row we have minimum 4, in next row we have 5, in next we have 6 and then in last we have 2. So what we are going to do? We are going to subtract these numbers from each row. Okay, so 4 from first row, 5 from second, 6 from third row and 2 from the last row. So this will be my resultant matrix now. Now I can see that I have 0 in my first row, I have 0 in my second row, I have 0 in my third row, I have 0 in my fourth row. Now I have to repeat the process for each column. So I'll identify the minimum value in each column. So these are the minimum value. In first column I have 0, in second I have 0, in third I have 1, and in last I have 0. So I have to subtract this 1 from third column. So because I'm going to subtract 0, there will be no impact. So what I'm going to do, I'm going to subtract this 1 from the third column so that there is an entry 0 in third column as well. So this will be my resultant matrix. Now this matrix is called my reduced matrix. But what about the numbers I have subtracted? That number is actually the minimum cost that will be there if I am traveling from any node to any other node. So that is my minimum cost, which is now fixed if I'm going to travel. Okay, so how to calculate this cost? This cost is sum of all the reduction elements. So what are the reduction elements here? It's 4, 5, 6, 2, whatsoever I've applied in rows, and then 1 that is being applied to column. So a total of 18. So this is my cost of reduction. Now I can say that I'm starting from my first node, that is A, and the cost associated with this is 18. So minimum, whatever, wherever I'm going to travel, my cost will be at least 18. In addition to this, I'll set another variable upper, which is being initialized as infinity. So what's the role of this upper here? Upper is basically defining the solution which I have reached, the value or the cost of the solution which I am going to travel and have reached to a solution, I'll update that upper. Okay, this is the cost which I found in my previous searching or previous traversing. Now, if there is any other path which is going to give me a value which is lesser than this upper value, then only we're going to travel the other path, or we're going to explore that. But here we are setting it infinity because till now we have not traversed any path. Okay, so let's see how we're going to traverse. There are three options: A, B, C, D. So through A, I can go either to B or to C or to D. Fine. Now I have to calculate the cost of traveling to B, traveling to C, traveling to D from A one by one. Now, if I'm talking about B, okay, so what I have to do, I have to make all the values of row A, that is this particular row, as infinity, and column B as infinity. So what is this infinity defining? That through A, I'm not going to travel to any other point because I have been traveling to B from A right now, and no other node will take me to B. So the path which are making me reach to B, I'm making it as infinity. So the row of A and the column of B is set to infinity. In addition to this, I have set infinity of path B to A because I am not going to travel from B to A because I am setting the path from A to B. So these are entries which are marked infinity. Now again we will reduce it. Okay, as you can see, there is no 0 in this row, there is no 0 in this column. So I'm going to reduce my matrix again. Now I'll come to a reduced matrix solution, which is by subtracting 13 and 5 correspondingly. Now the resultant adjacent matrix is this, and the reduction cost is 13 plus 5, that is 18. So we will calculate the cost of B now. So the cost of B is cost of A to B. So the cost of A to B was 0. Okay, and the previous reduction cost is 18, and the current reduction cost is again 18. So the total cost is 0 plus 18 plus 18, that is 36. So the cost to reach B from A is 36. Now we'll apply the same procedure to C and D as well. So let's have a look. To have path from A to C and to calculate the cost, we have to reduce this matrix again and make the entries infinity as defined. So I'm making the A row as infinity and C column as infinity, as well as path from C to A as infinity. Now there is no need of reduction as there is 0 in each row and each column. So there is no need of further reduction. So the reduction cost is 0. Now if I calculate the cost from C for reaching A to C, then I have to calculate cost of AC, which is 7, and then previous reduction cost is 18 and current reduction cost is 0. So the total cost is 25. Now for D, we have to make the entries infinity. Again, there is no need of reduction in this row and this row, but I have to reduce this row. I have to reduce 5 for this row. So the reduction cost is 5 here. Now we'll calculate the cost. So this cost will be 3 plus 18 plus 5, right? So this cost is 26. Now I have to see at which path I should go further. I should traverse to which node further. So I can easily verify that cost of B is 26, cost of C is 25, and cost of D is 26. So the minimum cost is of C. So I'm going to explore the path for C this time. Fine. Now I have to take the matrix which I have reduced for reaching to C for further calculations. Now, okay, so from C I can go to either B or D. So I'll make the calculations again for B and D. So this time I have to make the row C as infinity, column B as infinity, and path from B to C as infinity. Again, no reduction was required, so the reduction cost is 0. Now I'll add up the entries to calculate the cost. Now cost from C to B, the cost from C to B was already infinity. Fine. So infinity plus 25 plus 0, that is infinity. Now the cost of D is infinity. We'll do the same with D. So we have made the entries infinity. Now we have seen that no reduction is required. Reduction cost is 0. We'll further calculate the cost of D. This will be 0 plus 25 plus 0, again 25. So the cost of D is 25. Now we'll see where we have to explore further. So between B and D, I'll choose D to be traversed further because D is carrying the cost which is lower than that of B. Now we will take the matrix which was reduced for coming up to D. Now we'll make the entries for B because only B is the node left with us and this is only the path where we can go now. So we'll make the entries infinity correspondingly and then we'll see that no reduction is required. So the reduction cost is 0. Again we'll make the additions. So it will be 0 plus 25 plus 0, that is 25. So the cost of D is 25. Now at this point we have traversed all the nodes of my graph, right? So I have reached to a particular solution and solution cost is 25. So I will update my upper to 25. So at this stage, I know that I have discovered a path whose cost is 25. Now I'll look into node that to see or to verify that the cost by exploring other nodes could be less than 25 or not. So how I'm going to do this? I'll see to the cost of B and C. These are already more than 25, right? So I'm not going to travel this because I know that I have already retrieved a path whose cost is less than this, right? So in summary, I would say that we have started the branch and bound basics and we have started the traveling salesman problem in this video. Thank you so much.